All right, so where were we last time? We were looking at algorithms of the type which have S1 is xk plus alpha k dk, where dk is the descent direction and alpha k is the step size. What was steepest descent? So dk is equal to minus gradient. All right, and we saw something interesting about it. What was that? This is in fact, so what we showed rather was that pick any dk such that del fxk dk is less than 0. It's a descent direction. And among all possible choices, picking this gives you the largest degree. Now we're going to exhibit the problem you see using the steepest descent. It's not a fundamental problem, but does show up because of this particular property that you end up getting. So let's try to look at an example, and we'll see that in fact that is true always. Okay, so let's take an example to begin with, and we'll see the execution of steepest descent on this example. So let's say f of xy. See, in a single dimension, you won't see it. So you at least have to go to 2 dimensions. Is 4x square minus 4xy plus 2y square. I think this is the same function we used last time also. Okay, and let the initial point be 2, 3. So what is del f of xy? That's simple. It is simply 8x minus 4y, comma, minus 4x plus 4y. Right? So what is del of? So I should technically write x0, y0. Okay. So what is y0 equal to? It's simply 4, 4. All right. Now comes the question of step size. So what will be the step size? Alpha k. Will be minimizing what? So what do you want to choose alpha k to be? The one which minimizes f of xk minus alpha k, gradient of f of xk. Right? You want to choose alpha k such that it minimizes. So this is R min over alpha. So in this case, what will be that be? Can you just see? Minimize f of 2, 3 minus, let's call it alpha for the moment. Right? That's what this will be. So which is nothing but minimize this with respect to alpha, which is minimize f of 2 minus 4 alpha, comma 3 minus 4 alpha. And how would you find it? You essentially try to, looks like a convex function. You just try to equate this for the gradient to be equal to 0 as a function of alpha. Any guesses to what's going on? What alpha will be? If you want to do computation, don't do it. Then I'll write it. You can see it directly, then tell me. We did this last time also. That's what I'm saying. Can you guess it? This is what we. Sorry? So optimizing alpha will be, alpha star will be 1/2. Just basic algebra, there's nothing going on. Okay. In fact, this is a strongly convex function as a function of alpha. You can find this. So now what will be the update? So this you can find. You don't have to worry about it. So what will be an update? Update will be, next point is going to be x1 comma y1 will be x0 comma y0 minus half times, what was the gradient? Gradient of y0, which is, what are the points? 2 comma 3 minus 1/2 4 comma 4. To keep track of what's going. So we started with 2, 3. Now we landed up 0, 1. We'll do it one more time and then see something interesting will pop out. Okay, let's do it one more time. So now what will be x2 comma y2? Will be essentially x1 y1 minus alpha k del f of x1 y1. Where alpha k will be again optimized. So let's call it alpha 2 here. Okay. So what is del f of x1 y1? Now the new point is 0 comma 1, the function we have left behind. So let me just write this again here. F of xy is equal to how much? 4x square? Yeah, 4x square minus 4xy plus 2y square. So what will be my derivative at x1 y1? Be minus 4, 4. Okay. And again, we'll find alpha 2 such that argmin of f of will be 2 comma 3 minus alpha 4. And that will turn out to be sorry, what is the question? 0, what is my new point? 0, 1. Yes. Very good. And now the t will be 1/10, and the new point will be x2 is 2/5 comma 3/5. Okay, so 3 points. What are the starting points? x0, y0, 2, 3. What is x1, y1? 0, comma 1. And the third point is 2 by 2 is 2/5 comma 3/5. Geometrically, is there any connection between these 3 points?
Zero y0 and x2 y2, they have the same. As like they pass through this 0, 0, and they have the same. So they have those 2 points are the same.
Okay. What else? Connect the 3. Don't look at the pair. You can draw it pictorially. We're just, let's hopefully draw it correctly. So first point is 2, 3, 1. It is 0, 1. Say 2. Where is 2 by 5, 3 by 5?
It will line to the origin to pass. That's going to be very like, it will be very,
Still be wherever it is, wherever you think it is. It's
okay, maybe like, yeah,
2 by 5 is roughly
like,
close to,
bit lesser.
yeah. So here and slightly here. Anything noticeable here?
That's perfect.
Now is this, if you were at the talk, that's what you're trying to happen. You see some properties, you always want to think that is it universal or just because I'm running for a particular function. So this in fact is 90 degrees. You can check the inner product here. This is the property we'll try to prove, that the successive iterates have this relationship. They're orthogonal to each other when you're taking the steepest descent direction. Only when you take the full step in trying to minimize this. If you don't, then that may not hold. So it's every time, if you don't steepest descent direction and go as far as you can, then this property will hold. And this is where problems start for certain types of functions. If they're very narrow, this iteration could be very slow. That's what ends up happening. I'll tell you what narrow means. But for certain problems, this essentially, so if you had something like a minimization problem of this type, so this is, I'm drawing a contour. So the function has the same value on all these points. That's what it means. And as I make it inner, the value is decreasing. So you just think of it as going down like a cup and further and further. What this ends up doing is this goes here, then it makes a 90-degree cut, then it goes again 90 degree. And so it zigzags and goes towards the optima. This is one property, that's why steepest descent with full steps, like the optimized step size or full line search is avoided for. So if you look at a particular problem and see this is very narrow in one direction, these are typically avoided. If they're isometric, then things are much easier. But the property we'll prove is generic, that look at steepest descent and optimize the line search. This property always holds, and the successive iterates are orthogonal to each other. So any way to see that why that's happening is actually obvious from just the execution of what we did. Anybody wants to take a crack at it. Why should this be true universally, not for this particular example? The property is clear. Everybody understand what that means? It's very simple to state. Successive iterates are orthogonal in terms of their difference. You can even think of it directly in terms of the gradients in successive steps. So in this example, look at gradient of f at x0, y0 and gradient of f at x1, y1. Don't do many compute. I don't want to compute anything. Just see it, what's pushing you towards such a result. But once we select the gradient direction, we're doing some optimization. What is that optimization? Minimizing with respect to the step size alpha. And that pushes you somewhere. We're trying to find a minimizer there. What exactly happens? We put the gradient of that equal to 0 with respect to alpha. Does that give you any spark? Let everybody say it. It's actually, once somebody prompts you, it should be obvious that that's what is happening. So once you make the, so x2, y2 is x1, y1 minus alpha 2, the gradient at x1, y. Now, I'm also trying to minimize with respect to alpha 2. What will be the optimizing choice in terms of this x1, y1 and gradient of x1, y1? Now it's connecting itself, right, some way. So whatever the choice of alpha is, if I define a new function g, what is that function g for which alpha 2 is the minimizer? x1, y1 minus alpha times del f of x1, y1. So what is the property of the function g at the minimizer? Its gradient should be equal to 0.
So then inner product is.
So inner product of what and what is 0?
So you take f prime of this. So
Yeah.
So f prime of that.
Correct. It will get me second derivative. I don't want second derivatives. Okay.
We're just taking this.
First derivative. With respect to alpha.
So first we need to take f prime of the
G prime. Let's talk in G prime.
G prime of the whole thing dotted with f.
Why would that show up?
It's so we're taking f of
No, just look at the update. Update equation is x1, y1 minus alpha 2 gradient at x1, y1. Think of that itself as a function of alpha, g of alpha. Now finding optimizing alpha, what are we trying to do? We're trying to find the minimizer of function g with respect to alpha. That means at the optimizer, the gradient of g is 0.
So g prime of alpha 2 is.
So yeah, so what will that entail? So it's inbuilt because the way we are doing certain things. Okay, let me. I'll write the theorem statement at the end. Okay, so first the proof. It's actually instructive. So let's write what is my xk plus 1 minus xk and xk plus 2 minus xk plus 1. This quantity is nothing but before optimizing alpha k times derivative of xk with a minus. Similarly here alpha k plus 1 gradient at xk. That's my updating. I'm just rewriting that. Now what am I trying to do to find alpha k? What is alpha k? Where lies the answer? Sorry? Arg min of what? This function. What is my function? Right? Now can you give me that one line? Just remain, what remains now is one line. Given that this is true, what can you deduce?
F prime of this.
Yes, so what is not, yeah, let's call this function g or whatever you want to call it with respect to alpha. That should be 0. So what that will be?
So gradient of f of xk.
Gradient of f of xk. Keep going.
Times f prime of. Is that correct? Yeah, f prime of. Yeah. Gradient of the whole thing, right? Gradient of f. Gradient of g. Yeah.
Okay, let's not mix it now. I've not written g, so just tell me what it is. If you want to write g, I'll write g, but now there's no need to write
Yeah,
it.
f prime of xk minus the whole thing. You're taking a derivative of the whole thing, right?
Yes. So all I'm saying is alpha k is arg min over alpha of this function. This implies something. What is that implication?
The derivative of this with respect to alpha k is 0.
That we know, but what do we get out of it? Once I take the derivative, what will I get? Xk, all of this. Okay, equal to 0. Okay, what will you deduce from this? What is this term? You look at the definition. Right. So what do we get? This is essentially the property which implies that this is really the punchline. And from this, you can deduce that these two are orthogonal. Now, this implies that xk plus 1 minus xk dot xk plus 2 minus xk plus 1. So, what is the theorem statement? Theorem is, so this is called the ZigZag theorem. There are many ways to write it. Method of steepest descent follows the zigzag path. Now, this is slightly lower, okay, towards x. That is, you can write in either form, then del f of xk, del f of xk plus 1 is 0, or xk plus 1 minus xk. So this towards is not completely watertight. So for nice functions, this is true. But we haven't yet proven that steepest descent always converges. So that towards x star, take it with a pinch of salt, that whenever it's possible to do so. But this is a very interesting property. It is not obvious from before you start to look at it. You would always like to go as far as possible in trying to minimize, but that gives you a problem. So there are ways to slightly rein it in, not necessarily always go as far as you can in terms of your maximizing the step size. All right. So let's take an example to see execution of steepest descent. So the previous result doesn't necessarily show that steepest descent is bad. It's just showing for certain problems, the convergence could be slow. That's all. For quadratic problems. This is the most generic convex program you'll encounter. So what is the goal? Goal is to minimize f of x is equal to half x transpose qx minus b transpose x for x greater than. And q is positive definite. You can actually do this even when it's positive semi-definite. But for the moment, it's positive definite. So do you know what the optimizer of this problem is? You might have seen. We actually did it. So some Q transpose Q inverses get involved. So that is why, because of the inverse, you typically want this to be positive definite. So currently we'll only see. And what happens if Q Q is negative definite, what will happen? Minus infinity.
Yeah, sorry.
So unbounded below. So that's why we don't care about negative definite. And when Q is in fact positive definite, it has a unique optimals. Why is that? Anybody wants to? Actually, in the test, I wanted to put true or false. This particular course is tailor-made for true-false statements. Because some certain things you accept that gospel truth, sometimes they're wrong. I was hesitating because it's very easy to go wrong in a true or false statement. You either go true, it's like binary answer. So I hesitated, but it's a tailor-made course for that. Yeah, and why is it unique? If Q is positive definite, is it necessary for uniqueness? Strict convexity is enough. And strict you can show. It's true that it's strongly convex. Because you can simply take Q to be identity. Identity is the worst possible positive definite matrix, and you'll be able to do that. Okay. Oh, so let's see the execution of steepest descent. So xk plus 1 will be xk minus alpha k gradient of k. So let's call g of alpha to be f of xk plus, sorry, xk minus k minus alpha del of xk, and we would like to find alpha as before. So this will be half xk transpose. Let's make sure that I don't make mistakes. Minus alpha del f xk q xk, the whole transpose, right? Should be here. Xk without the transpose here. Xk minus alpha xk minus b transpose. Okay, so what kind of function is this? Now I need to minimize this with respect to alpha.
We can take the derivative first with respect to xk minus alpha. Then take the derivative.
What kind of function is this with respect to alpha? Yes. More important, is it convex or not convex? Because whatever we're going to do, we want to establish the fact that it's convex so that taking the derivative, in fact, we're hitting the global minima. Yeah, so why I'm trying to pay attention to this is that generally does this blindly without actually establishing the fact that it's in fact quadratic and convex, so you can do blah blah blah. So generally it's good to be honest. Is this function really, like sometimes some functions might look but may not be true. So it's just good to be aware that the fact that g of alpha is in fact quadratic and convex. Big people make mistakes. They'll assume the function just appears to be convex. What is there to be done? The papers will find mistakes of the type. Function is convex, so I can do this, blah, blah, blah. Turns out that maybe it's not true. Okay, so now we can essentially just do. So what is the form? G of alpha is A alpha square. A is bad because B I have taken. So A alpha square plus d alpha plus c. So which implies that alpha star is nothing but minus d over 2a. So we put back everything. What we end up getting is that the optimizing alpha is del fx transpose times del fx divided by del fx transpose q. That's my optimizing alpha. I'm skipping a step because that's just pure algebra. There's nothing to be done. So what does the algorithm will look like? The algorithm will be xk, xk minus 1 minus all of this del fx k, k over times del fx. Now you see why I needed q to be positive definite. It's sitting in the denominator. So if there was any even a zero eigenvalue, this could potentially create trouble. But all these methods actually, whenever there is an inverse involved, are typically avoided by solvers. Because even if they are technically defined to be positive definite, if the eigenvalues are very small, these blow up and create all sorts of trouble. So that's why there are lots of methods which completely avoid these inversions. But steepest descent will require an inversion. So in the next homework, I'll also give you a couple of. So most people are happy with MATLAB or some coding platform. If not, maybe this is the time. At least you should be able to execute something of this type. So input will be some function. Method will be some method, either gradient descent with particular steepest descent or Newton's method or something. And then you just execute and show what. All right. So be ready for that. Any platform, I don't care what platform you use Python, fine. MATLAB is the easiest. We have license. It's the easiest to. So if you want MATLAB access, just go to Ravi, he'll give you the access. Don't use cracked versions. That's my advice. Cracked versions of it. On campus, using illegitimate software is a serious penalty. So given that we have access and it's pan TIFR access, just make use of licensed versions. And if you're a Python user, then I don't have to say much. Okay. So now what we saw was step size selection. One option was to optimize over the chosen direction. It's also called by many different names, exact search or like exact search or some other names also it comes by. The second is somewhat guarded methods called, one of them is Armijo's rule. That's what we'll discuss next, and we'll try to see what guarantees we can get for Armijo's rule. So the J is supposed to be read as here, Armijo. So it comes from Mexican. So what is the rule? The rule is as follows. So the method remains as before, that xk plus 1 is xk minus alpha k alpha xk. You can choose something else also if you want, but if you're following gradient descent, that's what you use. All we're going to alter is the choice of step size, which is alpha k. Okay. So let S be the initial choice of alpha, that is alpha 0 is equal to S. Let beta belongs to 0, 1 and sigma belongs to 0, 1. Two constants between 0 and 1. So alpha 0 is S. At any time step, at iteration k, try to use alpha k equal to satisfying. Now this is the decrease condition. When we did the exact line search, we just went as far as we could and tried to minimize that function. Now we're not going to go as far. We're going to say, I should get at least so much decrease. That's what we'll see. So there is something to be said about this also. I'll come back once I write the decrease condition down. So what is the decrease we get? F of xk minus f of xk plus alpha k d, or d direction, or you can choose whatever you want, to be greater than equal to minus sigma. So sigma was the constant we started with. Alpha, which is what we are going to use, times the gradient times the current direction d. So let me just use another pen. Paste. I want to ensure that my decrease is at least so much. That's what this condition means. See, this is smaller. That's why the negative. Sigma is a constant. Alpha k is my choice. D is just a direction. So you can plant D equal to minus of del f of xk you want. I'm just giving a more general answer. So now tell me, what should be this choice of M I should make? So as M increases, what happens to this? Beta is something between 0 and 1. So as M increases, beta M goes to 0. S is some fixed quantity. So what's happening to alpha k? So you're sitting at one particular step k. So I've purposefully left out an adjective to be used. So what M should I use? Because the condition in the colored box need not be true for every M. The smallest M that satisfies. Okay, why? Okay. So why not then use S? Correct. So choose the largest alpha k for which this condition is true. Now, why am I always guaranteed that there exists an M for which this is true?
It's true for alpha k is 0.
Not 0. D is a descent direction. So there is at least some step I can take so that I can decrease something. In the worst case, as I said, if you already at the stationary point, it will be 0. So in the limit alpha k going to 0, you should be able to satisfy this constraint. So it could be that you have to choose a very large M for a particular, because once you are very close to the gradient 0, the M might be very large. Because you're insisting on making progress. And that's why that derivative on the f of xk sits very nicely. So look at the right hand side. Why the gradient is sitting there? That as you get closer to the optimizer, the gradient is going to 0. So the right hand side also is going to 0. So the demand is also becoming relaxed. And in particular, if suppose you hit x star at some xk, what would be the right hand side be? It will be simply 0, because derivative of f of xk is 0. And then I don't have to worry about anything. So that's why that takes care of it. So even though it's written as a negative of something, that negative of something becomes 0 at the stationary point. So I'm okay to do that. So this is called the Armijo's rule. So it's not as aggressive as the completely optimizing in the chosen direction. This slightly reins it in, but requires a sufficient amount of decrease. That's what it's telling you. Our original condition was that choosing a direction as long as the gradient of f of xk times d is less than or equal to 0 is a descent direction. Now we are demanding something more than that, but not as much as minimizing the function itself with respect to the step size. So it's in between. It's asking for something, but not as much as we needed earlier. This is what is very, so this is actually one which is used the most often, this rule. The Armijo's rule is typically what is implemented. We'll actually see a guarantee today when we execute Armijo's rule under certain condition. Other options are other option is something like diminishing step sizes, where alpha k is decreasing, but summation alpha k is unbounded. This also works. So for example, 1 by k. Okay, so I need certain technical conditions now to prove so. So maybe this will be the first convergence result really. But we can't show this for arbitrary functions. We need certain technical conditions, and we'll now try to write them down. So what do we want? Ideally, we have this iterative algorithm, xk goes to xk plus 1 and so on. What do we want it to happen? We want this to go to
X star.
x star. What is x star? Global minimum. Right. So, and what will stop that from happening? So we want xk's to converge to the global minimizer. You want this to happen. What are the possible roadblocks of this? Roadblocks. Sorry. Local existence of local minimum. That's one of them. Okay. What else can be? Really poorly written. And I was giving Gyan to my kid yesterday. What else can there be a problem?
It might happen that once it reaches a certain point, it just keeps alternating. Yeah.
Say this again.
The xk it might not converge at all, which is possible.
Okay.
It will reach, like for example, the algorithm that we are given in assignment 1. Might happen that like you're trying to like do the projection on those two sets. Like we might reach a certain stage where like we reach one point and then we project onto the other convex set and then we again project back. We just keep alternating between 2 points. We don't ever.
Okay. That's the more difficult setting. Think of slightly easier, like that doesn't happen. Where else can you get stuck? You could potentially get stuck at a stationary point. You can't avoid a stationary point, and that could be a local maxima also. So just look at any of these rules we have. They won't move. Once you hit the derivative 0, they won't really move. They'll just stick around. Okay. So what is the hope we can actually have? X star is a global minimum. Is it always possible to converge to that or achieve that? Looks difficult. But at least we should be able to get to stationary points. right? This is like the bare minimum we would expect algorithms to do. Beyond that, it's difficult because for a generic problem, it's difficult. Then you will enforce convexity, strong convexity, blah, 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 to say there are no stationary points or there are no something of that kind. Then automatically global minima will come. For the moment, we are not enforcing any convexity. But even to achieve or to converge to stationary point, do you need certain technical conditions or no? Are these yours? Any of yours? So do we need any technical conditions to converge to stationary points with any of these algorithms, or that is guaranteed? You don't think there are any problems? Or if you think there are problems, what kind of problems there will be? What could go wrong?
Technical conditions, either the boundary or the function has to be boundary.
Boundary of what?
The domain of.
This is unconstrained. We don't really.
The function has to be bounded, otherwise it gets increasing.
Assume that the optimizers are not like they're bounded functions. That's not minus infinity or plus infinity. That much you can assume. But what is the guarantee? Like, why do you think that algorithms of the type we looked at would converge to a stationary point? Why can't they go and converge to a non-stationary point? That's the question really we should ask ourselves. Why can't they have a limit point which is not stationary point?
Because like when you take the descent direction, for example, like the slope keeps decreasing, right?
Yeah.
Eventually it must come to zero.
Not equal to zero. That's the diminishing property we're asking for. That also is reduced. So it could turn out that you're converging but not converging sufficiently. You're not moving sufficiently close to where you want to move. So it could be that you're converging somewhere, but that need not be, the limit point need not be the stationary point. So it's not obvious that any of these algorithms you thought about will automatically just converge directly to a stationary point. And the reasons are of that type, that they might become orthogonal. The progress might become completely orthogonal. There's not sufficient progress towards the optimal. So that's one of the ways. What else can it be? So one set of conditions we'll look at today. There are other conditions also. These are called gradient related conditions. For short, GRC. Okay. And what does it mean? So for an algorithm of the type we have been looking at, xk plus 1 is equal to xk plus alpha k dk. We say that the GRC is satisfied if for any subsequence of xk, think of this as a sequence indexed by the little k belongs to capital K. So this is the subsequence I'm talking about, whose indices are coming from the set capital K, this is the sequence. I'm talking about a subsequence that converges to a non-stationary point the corresponding sequence dk to the same subsequence corresponding. Corresponding sequence dk is bounded and the derivative of f of xk times dk is less than 0, supremized over, so lim so of two conditions. What are the two conditions? So look at our iterative algorithm. When do we say that GRC is satisfied? So look at any subsequence of this sequence, which is going to a non-stationary point. If there is none, then we are okay. Look at that subsequence, and along that subsequence, the corresponding direction sequence, dk, should not go unbound, essentially the norm. And in more so, they should not become orthogonal to each other. That's what this means. I don't want this to be equal to 0. That's what this is controlling. The dk should not grow unbounded, and the inner product between the derivative and the direction should not become orthogonal to each
other. Why do we take lim sup instead of limit?
That's just technical. So if the problems are nicely well behaved, you might not need it, but just to make sure that the analysis goes through. Okay, so can you give me an example of an algorithm or choice of dk for which this GRC is satisfied? All you have to give me is a choice of dk. That's it. Because it's not saying anything about alpha k. Okay, and why would this be fine?
Because X stage converting to this stationary point, so yes, our stage is converting to a non-zero value.
Correct.
And my gradient of
so that the second condition is true. What about the first one? The dk is bounded.
Or we can use gradient divided by the norm of gradient.
So why are you moving away? Stick with it. So what he's trying to suggest is, if you just look at the steepest descent direction, his claim is that it satisfies GRC. Point is why?
The slope of the descent direction is
Sorry?
This case, like when it is equals descent slope, the slope is like high first, and then it keeps falling. It's not converging to a stationary point.
No, so if it's converging to a stationary point, what do we know? That the gradient is not 0. Only thing is it unbounded is the question.
It was unbounded, it couldn't converge.
That's all. So automatically unbounded is also ruled out. Zero is ruled out by the fact that it's non-stationary. Unbounded is ruled out by the fact that it is convergent. Because when do we say something converges? Converges to plus infinity is automatically ruled out. So that's why the steepest descent actually satisfies this condition. So now let's try to prove our first result really. All we'll need is GRC under Armijo rule. So GRC is for dk, Armijo rule for alpha k. And we'll try to prove that wherever it's converging, it cannot be a non-stationary point. That's what we'll try to prove. Okay. Fair enough. Let xk plus 1 xk plus alpha k dk. Let dk satisfy GRC and alpha k is chosen by rule. Then so dk satisfies GRC, alpha k is chosen using Armijo's rule. What we want to show that limit points of xk are essentially the stationary points of f. And that's the best we can actually hope for without putting any structure on f. We'll use contradiction to prove this. Okay. Suppose x bar is a limit point of sequence xk, but del fx bar. No. We'll use this fact. Somewhere we'll claim that the fact that it is not equal to 0 implies something. Now we are using update, sorry, the step size selection using Armijo's rule. So what do we have? So the Armijo rule implies that f of xk plus 1 is less than or equal to f of xk. Therefore, either the sequence f of xk converges to a finite value or diverges to minus infinity. You don't have to necessarily write the whole proof. You can always go back and look the video or something. It's up to you. So you don't. And at some stage, I'll give you this. So I'll be away for a week in between. So I'll just give you this and you can photocopy and circulate among yourself. Okay. So what does it mean? The Armijo's rule is telling us that we always have a descent direction. Essentially, so either this sequence converges to a finite value or runs up to minus infinity. Which case I am not interested in? This one really. If it's unbounded, I can't really do anything. So I will only be interested in when it converges to a finite value. So that's what we will be interested. So therefore, moreover, happening to my right hand today. F is continuous. This is okay. So x bar is the limiting point of the sequence, and f is continuous. So just by continuity, this is also true. So what does this imply for us? That f of xk minus f of xk plus 1. What is happening to this sequence? Yes, because this is going to a finite value essentially. So this is going to 0. This is really the punchline of this proof. That you're converging to a non-stationary point, but still this is happening. Right? So now, how do I invoke the Armijo's rule? Proof is rather long, but step by step we will go. Okay. So this is true by whatever we have set up for ourselves. What does the Armijo rule tell us in terms of this difference? It told us something about that how much I am decreasing every step. But this is telling me that it's actually going to 0. So these are at odds with each other. Unless, that's where the trick is, unless this is true. You see the connection. So we'll see the proof, each step will be fine. But more important thing is how the proof is built. This is telling you that this difference is going to 0. What does the Armijo's rule tell us? The difference is at least so much, finite quantity. And that finite quantity has a factor, which is the gradient at the iterate itself. Right? Let's go back to that here. So the iterate itself appears as its gradient. Now, if this is non-zero, the converging, where is it converging? F of xk is converging to f of x bar, at which point the derivative is not 0. But we know, because of that, we know that the Armijo rule should guarantee us something, a non-trivial decrease in the function. But this is going opposite it. This is telling you that that is converging to 0. So something is going wrong. That's really what the crux of the proof is. That the Armijo rule is guaranteeing me sufficient decrease, but because I have started with this hypothesis that the point where I'm converging to is not a stationary point, there is something going on. So that's what the proof is all about. Mostly technical, but main idea is this. Okay. So from the Armijo's rule, what do we know? That f of xk minus f of xk plus 1 is greater than or equal to minus sigma alpha k gradient f of xk and dk, and that is greater than or equal to 0. Sigma is greater than 0 by choice, right? Thus, because of the previous step, what do we know? That this difference is going to 0. Sigma is greater than 0. So what has to go to 0? The rest of the things have to go to 0. So thus alpha k del f of xk dk have to go to 0 from 1. Now let K be the indices, K is the set, index the subsequence along which xk converges to our starting point, non-stationary point. Now recall that decays satisfy GRC. So what does it mean? That the lim sup of del f of xk dk is less than 0 over k going to infinity, k belong to capital K. That's just by hypothesis that we have started with the fact that the gradient directions satisfy the GRC. Okay. So we have this equation number 2, we have equation number 3. If you put them together, what do we get? So let's call this. So let's call this equation number 2, this equation number 3. If you put 2 and 3 together, what can we deduce? Alpha k goes to 0. Okay, so now that what we have established. What's the handle we have for ourselves now to come up with a contradiction argument? So remember, we want to prove a contradiction that because the limit point is not stationary, something has to go wrong eventually. In between, what we have created for ourselves is that the sequence alpha k of your algorithm, which is chosen according to Armijo's rule, is converging to 0. So what? So all it essentially tells you that the Armijo rule is not choosing alpha k equal to s, but alpha k equal to some beta power m times s. That's all it's telling you. That after a certain time, essentially on this subsequence capital K, the choice of alpha k made by the Armijo's rule is not of the type s. It's some beta power m times s. That's all you can deduce from here. But because of the Armijo's rule choice, what do we have? See, it chooses the smallest m so that the step size is the largest. That's what Armijo does. So, because of this, 2 and 3 together imply that alpha k is of the type beta power m times s for m greater than equal to 1 for k belonging to capital K. That's all it means. So it's going to choose the m for which that condition is guaranteed. So one before that, what happens? If you're picking, let's say m equal to 2 you picked. Why did you go to 2? Because it did not satisfy at 1. So if I were to divide the choice of alpha k by 1 beta, that condition should fail. That's precisely what I'm going to do. And to do all this, I had to establish that on this subsequence, it's choosing alpha k to be of this type. It's not choosing this m equal to 0. So strictly, it's greater than equal to 1. Otherwise, I would not be able to do it. Okay. So now what we're going to say is, whatever choice you're going to make at time step k of beta, or sorry, of m, if you had chosen m minus 1, that would have failed. So this implies that f of xk minus f of, just pay attention to this, xk plus alpha k, actual choice divided by beta times dk would not have satisfied. So it is less than equal to minus sigma. The same thing, alpha k by beta gradient f of xk times dk. This is the really what we, so 2 and 3 imply that alpha k is of this type and m is chosen to be the smallest number that satisfies. So 1 before it doesn't satisfy, so you get a less than equal to sign. So it's each of these is very, very precise. That's what is happening. Okay. Now, do you see something interesting going on? So suppose I were to divide both sides by alpha k by beta and take some limit, not specifying what that limit is. What do you think? What do you think is going on?
Derivative of that.
Okay, very good. So what will you get on the left hand side?
F prime of x. In the direction.
Okay, so that's the left hand side. What about the right hand side? There is just simply minus sigma gradient of f of xk times dk.
The same.
Yes. Yeah, true. And all of this is makes sense because the gradient of f at the convergence points is also converging, right? So I can take limit that xk goes to x bar. So what do you essentially end up looking like? It is gradient of f at x bar times what? Times dk by norm dk. You can take norm dk, this, right? And dk also converges somewhere, let's say. So what will it look like? It will look like gradient of f of x bar times the limit of dk less than equal to minus sigma of the same quantity. And all of this makes sense because the gradient of f at x bar is not equal to 0. Otherwise, 0 less than 0 is like useless. So suppose we can get to that. Can you finish the argument? I'll tell you how to get to that much. But supposing we're able to show this, that f of x bar times the limit of dk is less than equal to gradient of fx bar multiplied by sigma times the limit of dk. That's what really you have to do. What can I deduce? Can you deduce that it's not a descent direction? The choice you're making of dk every time is such that it's a descent direction, right? What does it mean? That del of f times dk was always less than equal to 0. Does this prove it is greater than 0? Or greater than equal to 0?
Meaning minus sigma.
Yeah.
So the dk is also descent direction.
No, for the moment we've forgotten all of that. That's the whole point of contradiction. That we know that gradient of f times dk is in fact a gradient, a descent direction. But given that we started from the hypothesis that x bar is not a stationary point, can you conclude from here that in fact the gradient of f at xk or rather x bar times where dk is converging is in fact greater than 0?
How do we lim sup gradient of x dk is less than 0?
Lim sup of what, sorry?
Like the third equation.
Yeah.
So gradient of f of x bar times the limit of dk is also less than equal to 0.
Okay.
Multiply with the negative constant will get positive.
Yeah, but what is this equation telling you is the question. Because there the what we will do is eventually we'll take the limit separately of two things rather than the product. So just think of if you get a quantity which is of this type, gradient of f of x bar times some vector is less than, this is also minus, right? Yeah, this is also minus. So minus of, so informally I'm writing this, okay? So suppose you see that minus f of x bar times, let's call it d tilde. That's where dk converts to, is less than equal to minus sigma del fx d tilde. What can you conclude? And f of x, this is not zero. Just take it to the one side. Just 1 minus alpha times this quantity